Hi, everybody. Thanks for being here this morning. I'm Kyle, and I'm a software engineer at Google and an Apache Beam committer.
Hi, I'm Ismaël. I'm a software engineer at Talent. I'm part of this project of Apache Beam, and also I contribute to other projects in the big data space of Apache. So today we're going to talk about Apache Beam and a little bit, a tiny introduction to Apache Beam, but we are going to focus more on how we do the magic of running Beam code in Spark Runner, or that's concretely the main focus of the talk, and with the goal of showing how we support languages like Python and especially Go that may not be supported in the target system, but well, we'll go there. But before I start, just one question. Who knows MapReduce, Spark, basic stuff, like word count level, please? Okay, that's good. That gives me hope. Who knows Beam a little bit or has done something with Beam? Okay, so that's less than I expected, but still good. Okay, so we are going to talk then, and we have this introduction to Beam model and what is this vision and what is how it works. But sadly, we don't go deep into the details of the Beam model because that would be a complete presentation by itself. So Beam is an Apache open source project that is a top-level project since 2016. It was donated by Google and other partners like Cloudera and Data Artisans, now Berberica. And it's a general purpose parallel distributed programming framework, which means that it's in the family of Spark, Flink, and all of these things. But it's mostly two things. It has mostly two goals. One, to have a unified programming model, so it's a unified API, let's say, to do batch and streaming with the same code. And the second one is to be portable. And portable means two things. Being portable in the sense that we translate the code you write in Beam into the target execution system, for example, Spark, and also that we support multiple languages. So that's the overall goals of Beam. And for this first part of having a unified model for batch and streaming, Beam introduces some extra concepts into the programming model. Concretely, every element that you are going to process in Beam has an associated timestamp. And the idea of this timestamp is that you can use it to define when you do aggregations or operations downstream. Why? Because we are supporting streaming, so we don't know when is the end of the stream. So we have to put some way to decide when we do the operations and calculate results. And we do that we do this with three concepts. Well, the concept of windowing, when we define windows that can be closed with certain conditions. For example, a 10-minute window, and I get the results that I have in 10 minutes. We have also the concept of watermark that defines that is a progress concept that defines that we are not going to receive more elements, but this is not. This is an estimation. This is not something exactly accurate. And to adjust this estimation, we have the concept of triggers, where we can define, let's wait for more elements, or let's close this computation at some point. So, well, this is something you can find more in detail in a presentation of Beam. But in general, the idea to have here is that all these, let's say, transforms and operators are to play with the trade-off of latency and correctness. See? When we want to have output produced, so that's latency, and how exact we need these outputs to be. And so we have like knobs to play with that. So as I said, the goal of the Beam project is to support multiple languages, especially, so any user will write his program in one of these languages, and then these languages are translated by what we call runners into the target destination system. And that's some of the languages we support today. And the target systems, as you can see, most of the Apache most popular big data frameworks are there. So you have Spark, Flink, you have SAMSA, Gearpump, all the suspects. Okay, so how do we do that? We do this with what we call the concept of a pipeline. The idea here is that we have an input that normally is distributed database or a distributed log system like Kafka. And with this input, we just apply a series of transforms. So we can do operations like map in MapReduce, or we can do like reduce or group by keys, but also we can do time-oriented operations on these streams. But as you can see, it's just a directed acyclic graph, so not that special. So if just to remind, this is the classical word count. And what we are trying to do here is just to count words in a text. And in classical Hadoop, what we do is these three operations. We do a map just to produce one tuple of word and number of occurrences. That is one. Then we just do a shuffle, so we can have in a different machine the same results for each key. The same result. And then we reduce that in the destination machine. So that's basically how MapReduce works. In the case of Beam, we have two keywords to do this kind of operation. We have map elements, that is just a map that receives a map function. And we have sum by key, integers by key, which just applies a sum. So that's not so different. So if you want to see that in code, this is what is happening. We are reading a text file with what we call an IO in Beam, text IO, and we read this file. Then we have each line of the file, and then we split those just by space with a flat map function that for each line produces multiple words. Then we produce the tuple, that is a key value pair in Beam, KV, and then we sum this, and finally we output the stuff. As you can see, all these applies are like the arrows that connect the things, the pipes, sorry. But in reality, Beam has like lower level operators or transforms that we call primitive transforms. So these map elements is something that in Beam we call pardo. That is a more, like way more advanced map function that includes other concept of Beam. We have this group by key that is just essentially group by key, and then we have pardo that also does the reducing part. Why I'm talking about these primitive transforms? So, because when you write the code that I showed before, it gets expanded into this. So this is something that end users normally don't see, but this is an internal expansion of the transforms that everybody uses. And why we have these primitive transforms? Because for the end users, you have all these available classes, all these transforms and elements you can use to express your computation, and you have, of course, the classical suspects like sum, count, combines, that are reducers in Beam. And you have also flat map, all these things. But you also have the new ones in the right that are the ones that Beam uses to adjust the time operations I show in the second slide. So for windowing, to define triggers. But if you see all of this, would be too hard to translate. If we are going to translate each one individual of those, it's like an impossible task, especially if we have to target all these runners. So that's why we have primitive transforms. That are inside the model. But we also have connectors to all these systems. We have, of course, also most of the Apache data stores. We have Cassandra, we have the HBase, Kafka, Kudu, etc. And of course, also some of the cloud ones, like, of course, everything Google, because Google is the main contributor in this project. And we have a good chunk of Amazon stuff, too. And we support the classical formats, Avro, Parquet, also Apache projects. So all these operators and IOs, in the end, are just 5 core primitive transforms in Beam. Are these 5? So we have the read transform that basically is going to read data in parallel. So it's going to look for the partitions in the data stores and read the data. Quite essential one. We have pardo, that is just map per element processing, but with some tricks. We have group by key, that in the case of Beam has a special thing, is that since we have this concept of windowing, we need also to group by window. So we group by key and window, so we have all the results in the right place. We have flatten, that is just union of collections, and we have assign windows that allows us to assign the elements into the correct windows they should be in. This is also to cover the streaming part. So why I'm talking about all of this? Because this is, I'm going to show essentially how the runners work, but in the case of Spark, it's going to be like that. You just receive the Java code, and then there is this translation process that's going to create, like, let's say, rdd.map, blah, 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 .map, group by key, all these Spark operations. And this is relatively straightforward to do because we are calling Java code, and well, all these target systems are Java-based. So it's just a question of wrapping stuff and calling it outside. So in the end, what we want to do is something like that. Of course, this is not exactly how it's in reality, but just to give you an idea, you can see in the down part the equivalent code of the word count we had in Beam, but now in Spark. And as you can see, it's like it kind of translates directly. No, you have all these operators in all these transforms in Beam, sorry, that become these actions and transformations in Spark. So that's the general idea of what runners do. And why we are talking about all of this? Because our goal is to run Python and Go, but as you see, we are not there yet. We have all this Java stuff that maps naturally. So now I'm going to talk a little bit about the Spark runner. So of course, most people probably here know Spark. And why Spark is a destination system for Beam pipelines? Well, first, because it's the most popular big data framework. So something that if you have a Spark in your company or a Spark cluster or a Hadoop cluster, probably that would be the easiest way to get into Beam. Second, because Spark supports multiple resource managers, so target systems, so now even Kubernetes, so you can run in Hadoop, but also in Kubernetes, so that's a great thing to have. Also because there is a rich ecosystem of tools in Spark. That's something that most people, don't consider that much, but it's super important. We have projects like Livy that you can use to submit pipelines in a REST API, or tools to monitor like Critius Baobar. So Spark also has good tooling around. And of course, because if you are in your company, you have some support contract with one of these vendors, well, you also are somehow obliged to live with Spark too. So, and even now, there is a serverless offer by Databricks that we also have tested with Beam and works correctly. So the Spark runner, as I said at the beginning, was donated by Cloudera, and it originally was based in an RDD and DStream translation. That's the older API for Spark. At this moment, there is an ongoing work into a new runner based on the newer APIs, but for the sake of this presentation, we'll focus on RDD and DStream. It's one of the most mature runners, let's say, that's been battle tested somehow by people in all these companies. And there are really interesting use cases already of users of the runner, especially, this Cesnam group from Republic Czech. They are like an search engine, and they index a lot of data there. We have these GBIF people who also do how is the name of that? Biology observation of species based on that. So they're cool use cases. Okay, so I am just going to mention this quickly because you will probably see this afterwards. These are the operations in Spark. Basically, Spark also represents the data as a distributed collection that they call RDD. And with this RDD, you can do transformations of the data that there is there and actions that materialize this data. If you see these concepts maps with the Beam concepts, and they also have this concept of broadcast variables there are read-only state, let's say, that you can get into each worker. And we have this context that allows you to connect all this stuff together. Why I mention this? Because we are going to see now how we translate from Beam to Spark in the general way. And this is important because this is like the first step that we have with the runner, and will connect with the new translation for Python and Go. So as we mentioned before, we had the 5 primitives. So we are going to go into each one quickly. The first primitive is read. So as I said, what we are trying to do is just to read each partition in parallel and we have this computation executed. I mean, let all the data ready to be computed, sorry. There is one hidden internal secret of Beam is that every element on Beam is mapped or lift into a window value representation. Why is this? Because I said that we should have always a timestamp. We have the original value that you play with. All this is internal. It's just to give you an idea of how it works and that you can measure also the minor overhead that there is there. We have also the windows this element belongs to and pane information for materialization, for materialization, let's say. What we do in read actually is just to create an RDD. That's exactly how an RDD works. RDD has a method get partition, so we are going to map the read function from Beam into the get partitions method of Spark, so it's pretty straightforward. We have then to translate pardo. Pardo is a more complicated function. Pardo in Beam has a life cycle. And, well, if we translate Pardo, we have to respect that life cycle. We have also the concept of bundles, and also we have to decide how we bundle the elements. A bundle is like a little group of elements that can be small, for example, in the case of streaming, because we want to produce data downstream as fast as possible, or can be larger in the case of batch. And we have other stuff like metrics, state, timers. It's like a big Swiss Army knife of Beam. And in Spark, this is basically a big flat map and some other maps, minor maps to adjust things, map partition especially. And also use broadcast to get these side inputs that can be collections that you need to compute things, for example, like for joins. Then the next transform that we have to move into Spark is group by key. As I mentioned, we have group by key and by the window. So the clever hack here is just that we add the window to the key, represent that as bytes, and that's the new key, and that's mostly what it does. But group by key also has to take care of all these timestamp-based semantics, so it has to adjust times, it has to remove drop late data, because we don't want to shuffle more data than we should, and it has to decide also how we're going to trigger the results. Essentially, all of this is done by some maps, by a map, and then by the group by key. Finally, we have another one. This assign windows is the simplest one, let's say. We are just going to put one element into multiple windows. So basically, it's a map function that does this. Why this? Because, well, as you define the window strategy, that's something you may need. Finally, the flattened transform is just a union of collections. So this is quite straightforward to translate in Spark because we already have RDDs of the same type, and in Spark there is this union operation, so translation is just an union. Cool. So we have finally do the complete translation, but the key part is that we are calling Java code from Java. So this is straightforward. More concretely, we have these user-defined functions. It's the most critical part of the code that we end up putting into the executor machines, thanks to Spark. But what will happen if we need to do now this with Python or with Go? So now Kyle is going to talk with you about that.
Thanks. Okay, so so that was the Spark runner basically as it existed until earlier this year. It worked well for everything Java, but in Beam, one of the, like Ismaël said, we have these two levels of portability, right? So we had all of these different execution engines. We had a Spark, we had Flink, we had Cloud Dataflow, and a whole bunch of others. But then we also had additional SDKs, which are different implementations of the Beam model in different languages. So Java, Python, and then Go is another SDK that's been added recently. So then the question becomes, how are we going to then support all of these different languages on all of these different runners? So that is a tricky question. So with Spark, of course, you may know that there is something called PySpark, which is Spark's Python integration. So your first thought when translating from Beam to Spark might be, well, why don't we just use PySpark? And so this is kind of like maybe a little example of what that might look like. But there are a few problems with that. First off, doing this for every target language and runtime is completely not scalable. If you multiply the amount of SDKs we have by the number of execution engines we have, it just became completely unrealistic to build and maintain all of that. The second thing is that some target systems don't even have the targeted API. So for example, with Spark, we have PySpark, but then what about Go? There's no Go Spark. So that would just be impossible. There would be no way to do that. And then that was also the case, for example, with Flink, which did not have Python support. I believe they're adding it, but in the past it didn't. So the question becomes, how do we do this? And the answer is basically the subject of most of the rest of this talk, the Beam portability API. So this is a well-defined language-agnostic way to represent and execute Beam pipelines. So basically, what that means, the keyword here is language agnostic. So this is going to work for all of the SDKs, and it will scale. And then we also need to have a bunch of infrastructure related to this that we can reuse, which I'll talk about in a minute, in order to get things running on a language-specific environment. And then there are a bunch of challenges with this too, some of which we have pretty much resolved, and others that we are still working on. But a basic idea is, so we have to have an execution environment for this stuff. If you know about Spark, you'll know that it's basically all JVM based. And even things like PySpark are often going to use things like Jython, which are still JVM based, even though they're Python. So for doing languages like Go, this becomes a little more tricky because there is no Go integration with Java as far as I'm aware. So the challenge then is we need to support multiple languages. We need to somehow run this Python, Go, or whatever it may be on this in this Spark environment. And then there's also some other things to consider, like, of course, performance is something that everyone is naturally always worried about. And we need to make it easy to evolve, easy to scale, not too much of a pain to develop. And another thing that I might add to this is we need to keep the operational complexity to a reasonable minimum, because as you'll see here in a minute, it gets a little bit complicated. So basically, the way this works is we're going to end up using this concept of an SDK worker, which I'll elaborate on here in a second. But basically, we're going to shell out the work of doing user code to this SDK worker. So this is, again, what I talked about a little bit just now. But basically, we had Java and Scala and SQL all running on all of these runners, which was great. But then earlier, we only had Python and Go running on Dataflow and Flink, and not all of these other things. So enter the portable Spark runner. So this is very similar to what Ismaël just talked about with the existing Spark runner. But there are some key differences, as we will see. But a lot of this, I have to give credit to the folks who made the Flink portable runner. because Flink, again, as I mentioned in the last slide, was the first open source runner to use this new portability framework. So they got Python working first, and we were able to leverage a lot of that work to get the Spark runner working. And it basically proves the concept of portability, that like, yes, this is tenable to develop this for all of our desired execution engines. So it's, like I said, it's going to reuse a lot of stuff that Ismaël talked about earlier. And it is still based on RDD. And for now it is batch only, although streaming support may be coming in the future. We will see about that. And it's been around since the Beam 2.14 release, and I believe we're on the 2.16 release now. So still relatively new, but yeah. So this is the same 5 transforms that we talked about earlier. And out of these, there are at least 2 that are pretty much the same, those being group by key and flatten. So the implementations of group by key and flatten that he talked about are pretty much the same in the new portable runner. But then we also have a few differences with read, which I won't go into because that's a whole talk unto itself. The main thing I want to focus on is the pardo, which is basically how do we execute the user's arbitrary code in their transforms? How do we run that? And so that is the big question. And so the answer is, well, first things first. First, we need to be able to represent a Beam pipeline in a language agnostic way. And so the way we do that is with protocol buffers, which, as you may know, we use for many, many things at Google. But basically, yeah, protocol buffer. So our pipeline becomes a protocol buffer. And then we are going to, so we have all these APIs here. 3 APIs are listed. These are all gRPC and protocol buffer based. So we are going to first translate the pipeline into a protocol buffer. We're going to submit it to this thing here that we call a job server. And then we are going to, from there, we are going to translate the pipeline into Spark and run it on Spark. And so this is kind of an expansion of the previous slide. This is what happens after we submit it to Spark. So you'll see here that I've coded things as language specific and language agnostic. So basically what would happen is you would submit your Python pipeline, and then it would go to the job server, and then it's going to go to Spark. And basically what Spark will do is when it sees a pardo function, it will then shell out to these SDK harnesses via another one of our APIs, which again is mostly gRPC and protocol buffer based. So that's our so-called executable stage function that's going to run user transforms. It is basically just a very, very fancy Spark flat map function, and it's going to handle all of your user code, whether it's Python or Go or whatever. And so what will happen is we have a few special things for side inputs. Again, still going to use Spark broadcast variables, as was mentioned earlier. And then there's going to be some special stuff with windowing and watermarks, but that's pretty straightforward because, like I said, we're only doing batch for now, and most of that kind of stuff is useful more for streaming. So we're going to essentially send from here, from the Spark flat map function, we are going to send all of our work requests and input data to the SDK harness, which I've mentioned a few times, and that's going to actually execute the user code. So the SDK harness is a rather involved piece of machinery, shall I say. There's a little basic diagram here of how it works. But essentially, what it's doing is it's going to send all of its data from Spark to the SDK harness, and then all the work's going to happen, and then it's going to send back a result, essentially. So this is where there's a little bit of configuration to be done by the user, because the SDK harness can run in a number of different places. We wanted to give users the flexibility to do this in different setups. So the main way and the kind of the preferred way is to run it in a Docker container. And we are now providing container-based images that contain all of the Beam stuff that it needs to run transforms. So basically, you just have to add in your dependencies, like your Python packages or whatever, for example. But then that will take care of the rest for you. There's also a few other options for different deployment strategies, but Docker is the main one. So this runner, we've tested it. We just want to point that out. So basically, when you submit a PR to Beam, it's going to be validated now on both the classic and portable runners. And we also have Go integration tests, which is cool. So it runs on Go too. And now Go integration was basically free, because once you have all of this portability stuff in place, like I said, it becomes a lot more scalable. You can just add on new languages. So if anyone wants to write a new SDK, provided they keep the whole Beam SDK contract, it will be able to just work with this basically without any effort on our part, which is great. So for a little bit of an idea of how this might be used, I'd like to bring up the example of TensorFlow Extended, which is a sub-project of TensorFlow, which I'm sure pretty much everyone here has heard of. But basically, the idea of TensorFlow Extended is it's going to take care of a complete end-to-end machine learning pipeline. So whereas TensorFlow itself is mostly concerned with just the training of an ML model, TensorFlow Extended is going to be the whole pipeline. And we use this within Google quite a bit, and it's also started to get used by some of our partners in industry. So basically, TFX pipelines are going to be a set of components, which I'll have a diagram of in a second. But basically, you are free to use TFX in a complete pipeline, or if you just have pieces of it that you would like to use, you can also use them individually. So kind of cool. And then Beam is really what powers TFX, hence why I brought it up in this talk, because a lot of the TFX components are actually based on Beam, so much so that in a previous presentation, I think this summer here in Berlin, there is this quote: "Without Beam, we wouldn't have an open source TFX," because it's really just what makes that possible. So as an idea here, we have all of these TensorFlow extended components. So we have data validation, we have transforms, and then we have model analysis, and all of these. And data ingestion too. So all of these are based on Beam. These are all libraries in TensorFlow Extended, but they all use Beam under the hood to provide a lot of flexibility. And this is really important because, like I said, we do this in Google, and we also offer it as an open source product. So that means that it's important that it runs both on Google's own proprietary infrastructure as well as whatever kind of setup you might happen to have at your company or organization. And so in order to do that, we use Beam because, again, it is portable between all of these different execution engines. So the thing also about TFX is that it is all Python libraries. So when we wanted to run it on Spark before, we couldn't because it only supported Java. But now that we support Python as well, you are able to run all of these TFX libraries without modification on a Spark cluster, which is great because no one wants to have to rewrite a library that is this involved for every execution engine. So just a little bit of an idea of where we're going with this whole project. We have a few more features to implement. It is mostly feature complete with the essential features of the Beam model, but there are some new cutting edge features we would like to add. Streaming support is the big one in bold there. Yeah, so we do have streaming support for Python on Flink, but we haven't added it to Spark yet. So maybe we will get there at some point. And then performance analysis is something everyone always asks about naturally, and we are working on that. And then of course better documentation probably could be said of anything, but yeah, we also want to make some usability improvements so that it's easy for people to get up and running with this. As you might have noticed from the previous slides, there is a little bit of complexity added with this whole portability infrastructure. So we want to make sure that that is as seamless as possible for end users, so they don't have to worry about that stuff as much as we possibly can. And we'd also like to kind of document how to use this in cloud providers, another thing we're working on. So yeah, so if you are interested, then we have the link here for the landing page for the Spark runner. And we eagerly anticipate your code, ideas, documentations, tests, bug reports, complaints, opinions, anything. Yeah, so you also can subscribe to our user and dev lists, and we'll be happy to answer any questions there, or you can join the Slack channel. So yeah, thanks everyone.
Any question? Anyone have?
As far as I know, Beam is still in the preview mode or version. So my question is, where is it planned basically to release stable version?
Actually, I don't know if I understood. You said that there's not a stable version of Beam, you mean?
I think on the website I saw that it's
No,
in the
no.
preview
We
mode.
actually we have a stable version since we did the top level process in Apache. That was the release version 2.0. We have, however, some APIs that are experimental. Notably, all of this stuff is still experimental because it's ongoing work. But all the core transforms are quite stable, so no, this is already stable.
Okay, thank you.
Just a question to you, to Google colleague. Could you explain a bit more? I didn't get how you achieve the language agnostic. So, from my understanding, in some place you should somehow either translate the code from one language to another, or use some independent format. Could you please explain a bit more in this?
Yeah, so actually we do no translation whatsoever. The code is just exactly as you write it, it is run. So it's basically what's going to happen in the SDK harness that I talked about is it's going to, it's language specific, so based on what language you're using. So like there's a Python SDK harness, a Java SDK harness, a Go SDK harness, and so on. And so when you submit it to, for instance, a Python SDK harness, that SDK harness is going to know how to run Python code. So it will just run, basically it bundles Python on a very basic level.
But in this case, you basically need to support all combinations between languages and target systems, or I'm wrong?
No.
So if you support a new language, let's say Scala is already in the list, and with Spark, so Apache Spark, you for example support Apache Flink. How you do it?
So the answer is that the SDK harness is actually shared between all execution engines. It's not really Spark based. Yeah, pretty much independent from Spark. There naturally has to be some integration there, and that is going to be runner specific, but the SDK harness itself is its own thing.
Just to complement, I just wanted to show this slide because it could maybe help to make sense. The SDK code that you write in Python, in the end, is going to be executed inside the harness that is Python specific. So let's say you want to create a .NET support, for example. That should be pretty cool. Then you have to write this SDK harness and provide the APIs to connect. But all the rest of the machinery, you see, only the pieces in orange is what you have to do. And then it will be supported by Flink, Spark, all of the others.
But SDK API is the same.
You have
so
to, yeah,
output.
it's the same, but you have pretty
So
much to
just-
define the same, yeah.
And how large, how big, how many lines of code is in SDK?
And the harness, I mean, when I say SDK, is the user APIs. The harness is the set of services that Kyle showed that allow to pass data and control commands, let's say, to execute this data with this function. Well, I don't know the size, but it's a lot. Yeah, it's definitely big. Yeah, it's a lot of work. It's not so trivial to do. Yeah.
So continuing on the same question, like you also mentioned, like you had protobuf. So how is that helping in the portability part? Like, if I understand correctly, it's just a data format, right?
Yeah. So basically, you're just serialize. You write a pipeline in Python or whatever or Java, and then it serializes to kind of the same protocol buffer format, no matter what. So it's basically you're just essentially serializing the pipeline in a way that is common between languages.
To complement for example, you are not, as we mentioned before, we are not rewriting stuff. So it's the whole code that is just passed as bytes and abstracted in the other side. So, for example, because
Like
there's no other way
just
to
in
do
case it might just have been JSON as well. It doesn't make a difference here, right? Like just to yeah. Okay.
Yeah, definitely.
Yeah, I have a question. If it's possible in the future to create a service, for example, a cloud service, which would be the Beam execution environment, and you would also have to create a pipeline and a jar without any runner inside, and just deploy the jar with the pipeline to such a service, a cloud service, for example, on Google Cloud or AWS.
That sounds maybe similar to something we're working on. I don't know if it's exactly what you have in mind, but basically you can essentially now bundle. This is something we have for Flink, but not for Spark yet. But we're working on that. Basically, you can bundle everything into a jar that is essentially the same kind of jar that you would execute on any Spark cluster. And so there's basically nothing that you would have to add to that.
Yeah, but because currently, if I want to deploy my Beam pipeline to AWS, I use Flink Runner. So I have to create a EMR cluster. Then I have to run Flink inside, configure the Flink, so the memory and the storage for the Flink and so on. And the Flink is running on Hadoop. And I deploy the jar file with the Flink runner inside the jar file. Yeah. So the question is, if it's possible to create a service where I wouldn't have to care about all of the stuff in between, and just to give a jar file with a pipeline and don't care what is underneath, if it's Flink, if it's Hadoop, and so on and so on.
Okay, so well, actually Google offers a service for that. There's Google Dataflow. If you are in the Google platform, it's exactly how you describe. You don't care about the cluster. It makes everything by itself. Of course, if you are using one of the open source projects, well, you have to rely on that manually. I just mentioned at some point that for the Spark runner, you can also use Databricks, the cloud service they have. They do exactly the same thing you propose, but you have to package Spark in all this stuff in. But there is not, as far as I know, anyone working on a service like that, but definitely you can do it. I mean, and you can even create a new runner that doesn't have any of this legacy, but is created just to work on Beam. You can imagine doing that in WoW, but this is a huge project that I don't know if somebody will take.
So, as I understand, that portability stuff also is for Java right now, right? So also the Java SDK. So does it mean that if I have like, I don't know, the Spark cluster and I want to run Beam pipeline written in Java on it, I still have to install something of that Spark cluster, right? This SDK hardness, for example.
So you don't actually. There's two options there. You could just do the non-portable version because that's still around. And if you're using Java, then there is no reason not to do it. But then the second thing is that so you don't. I won't say you actually have to install the SDK harness yourself because again it's just a Docker container and we are publishing images for them now, so it will get them automatically, and it should be able to, if it's Java, it should be able to get your dependencies for you, so you shouldn't have to worry about that.
There is one thing that we already heard from some customers is that, people who run in Hadoop, for example, some of them are resistant to have Docker at the moment in the same machine in worker. So, but in theory, you can also use processes with this. I mean, there are like different environments, so that could be an alternative. But that's the only dependency, a part of the Docker images that they are already packaged.
And this is, again, kind of an ongoing discussion about how to make this more usable. So if you want to, you can share a message on the dev list, and we'd be happy to discuss your specific deployment needs and all that. Because we want this to work for everybody. But yeah, again, something that's ongoing discussion.